Hi everyone, and welcome to Erik's Electronics Workbench. So you can see we're not at the bench for the start of this video, but instead in a communications shelter, and the power supply that we're looking at has a problem and has failed. So let's get started with the troubleshooting and repair on this power supply and get it back into service. Here we are looking at the main DC power supply in this communication shelter. Now pardon some of the other background noises and distractions. It's quite windy here and there's a number of other noises in the background, so hopefully that won't be too much during the course of this video. So this is a power supply model PP-4763A GRC. There is also a non-A version. They're very similar power supplies. There was a difference in the circuit breaker design and some other minor changes that were made internally. Now this power supply has an AC input of 115 volts or 230 volts. It's currently set up for 115 volts. Under full load it will draw 23 amps at 115 volts or 11.5 amps at 230 volts. It'll operate on 50 or 60 hertz and it's single phase. The DC output is adjustable from about 27 to 29 volts and it's typically set at about 28 volts, and it will supply up to 50 amps continuous, so it's a very capable power supply. It's also very heavy, about 125 pounds. You can see the power supply is bolted into position on those bottom supports. So to service this power supply, I'd rather not remove it from the communication shelter. Again, it's very heavy and pretty awkward to remove it. A lot of cables attached behind it and so on. However, the front panel hinges forward and the top cover is removable, so I'll start by doing that to gain access to the internal electronics. There's also a main control circuit board that plugs in, so if the problem looks like it's on that circuit board, I can unplug it and then take that board to the workbench to continue working on it and troubleshooting it. So the story with this power supply is that it was functioning, and then all of a sudden the output started to surge with voltage spikes, and the voltage was increasing, and then all of a sudden the power supply just shut down, the main breaker shut off. This power supply has an overvoltage protection circuit in it, so it basically crowbars the output or shorts the output if an overvoltage condition occurs. That forces the power supply to draw a large current, which then makes the main breaker shut off. So that's likely what happened. When I looked at the power supply initially, I turned the main power on and the breaker just snapped off right away. So I thought, well, okay, that confirms the issue. But then now today, several days later, when I came back to look at the power supply, I turned the main power on and it was completely dead. There's a cooling fan that turned on, but there was no DC output whatsoever. And then I turned it on a second time, just cycled the power off and then back on. And the power supply did turn on, but the voltage seems to not be stable, and it looks like it's increasing, and I suspect if it is left to run, it may trip that over voltage condition again. So it's interesting that it kind of goes between a number of extremes, from no output to then suddenly having an output. So it'll be interesting to do some troubleshooting and find out exactly what's causing this problem. So I have my Fluke digital multimeter connected to the DC output. It's attached to another cable within the communication shelter, but it just goes to the output of the power supply. So I'll turn the main breaker on and we'll look at the output and let's see exactly what it's doing. So I'll reach over here and get to that breaker and we can see what happens here. Okay, so we can see there is the fault there. The power supply just tripped off, so it looks like it went into an overvoltage condition, or certainly something caused a lot of excessive current draw. There are no other loads turned on within the communication shelter, so the fan that you hear running is within the power supply itself, but there are no other external loads connected, so nothing else would be drawing any kind of excessive current. And you could see the voltage looked like it was fluctuating a little bit there, and then all of a sudden it tripped and turned off. So it does confirm the problem and it's still there. So the next thing that I will do is to open up the power supply. So I'll work on that and I'll reposition the camera once I have the power supply open. I now have the power supply opened up to gain access to the internal components. So you can see the front panel is hinged forward and the top cover has been removed. So over here is the top cover, and you can see the cooling fan right there. So I have the voltage regulation circuit board removed. That's sitting right there. And you can see next to it is the front panel DC voltmeter. I noticed that voltmeter was sticking, and it looks like it has an issue going on there, so that needs to be addressed as well. So I looked around inside the power supply, and I don't see anything obvious as far as overheated components or any connections that were loose or anything like that. So because it seems like a voltage regulation problem, I'm going to start by troubleshooting and taking a closer look at that voltage regulation circuit board. So I'll take that circuit board and the meter, and we'll go back over to the workbench, and we'll continue with the troubleshooting at the bench. Here's a view looking down inside the top of the power supply. So you can see on the left-hand side those two large bus bars. Those are joining several capacitors that are used for filtering. In the center, that slot is where the voltage regulation circuit board plugs in. There's a connector down at the bottom of that opening right there in the middle of the shot. You can see that large inductor down there, a lot of iron in that inductor. It's part of the voltage regulation and filtering circuit. That black wire right there with the plug on it is for the fan motor. Terminal board over here with some resistors on it, a large power resistor over here on the side. You can see that power SCR back there, Q2. That's the crowbar circuit for the over voltage protection. That SCR acts as a short circuit across the output terminals if that over voltage circuit trips. You can see the main power transformer right here. Again, a lot of iron in that transformer, very heavy. Over here, some heat sinks with the main rectifier diodes. Another inductor, L2 right there. Now, not visible from this angle, it's really down inside the power supply a little bit further, but there is another very large power SCR that's used for the voltage regulation control. We'll take a look at the schematic and you'll see exactly how that's used. Again, I can't really see it from this angle right here, and you'd have to pull the whole power supply out to be able to look down into it further. But this power supply is not a linear power supply, and it's also not a switch mode power supply. It uses SCR switching to control the output voltage in a rather unique way. So we'll take a look at the schematic and see exactly how they do that. Here's the voltage regulator circuit board as removed from the power supply. So before I discuss what repairs I'll be doing on the circuit board and the issue that I found, let's turn our attention to the schematic and see how this power supply functions. Now, if you're following along and working on one of these power supplies, please know that you do so at your own risk. The power supply contains numerous areas of exposed AC line voltage within the power supply, and the power supply is a very high current design, which of course has its own risks just with that design aspect as well. So be careful and stay safe, and again, if you're following along, you do so at your own risk. So looking at the schematic, we can see the AC line is brought in right here through some filtering, through the main circuit breaker, which is on the front panel. You can see both sides of the AC line are switched, which is good practice because this can operate on 115 volts or 230 volts. At 230 volts, you have two hot AC lines, so you'd want to switch both of those lines. The AC is brought into these terminal boards right here, which are have jumper links on them that can be reconfigured for the high or low voltage operation. You can see the blower motor right here, AC operated motor. And over here we can see there's an interlock switch on the top cover. So when the top cover is removed, the switch closes, and what happens is AC line voltage when the breaker is closed is applied through this switch, through this coil, which is integral to the circuit breaker. It acts as an electromagnet, and when this coil is energized, it shuts off the breaker, basically forces it to open. So what would happen is you would turn on the breaker, and immediately this is energized and the breaker would snap back off again. So very nice safety feature. So this is that very large main transformer within the power supply, T1. You can see right here on the secondary side, this is the high current secondary winding for the main output. And over here, there's two auxiliary windings. This has a center tap. These serve to power the voltage regulator over here, the voltage regulation circuitry, which is on that circuit board I just showed you. So these are very low current windings over here. You can see these come in over here to a full wave bridge rectifier down here, and another full wave bridge rectifier up here, and then the voltages continue on through the regulator circuitry. But looking back over here, you can see on this secondary, we have CR6. CR6 is a transient voltage suppressor. It serves to suppress or clamp any high voltage spikes that might appear on the secondary. Okay, they just clamp those voltages down to a safe value. Right here is another full wave bridge rectifier. These diodes are on that large heatsink that we could see when the front panel was open. So this is the positive output from the bridge rectifier. This is the negative output. You can see the negative output comes over here, comes down through an inductor right here, very large inductor that's in the middle of the power supply, and then basically comes down here to the negative output terminal on the power supply. But over here, the positive output comes down through this SCR and then continues down. I'll discuss what happens down here in a little bit, but right here, this SCR is the main voltage regulation control in the power supply. So the positive voltage right here, you can see there's no filtering at this point, okay? The filtering is occurring down here. So the voltage at this point is a pulsating DC. You can think of it as just pulses like this that are just, okay? So as those pulses apply to this SCR, to the anode on the SCR will act as an open, okay, until a control pulse is brought in on the gate. So if you're not familiar with how an SCR operates, the SCR doesn't conduct until a voltage is applied to the gate, and once that voltage is applied, it can be removed. The SCR will continue to conduct until the voltage on the anode falls to a very low value, basically near 0 volts. And once that happens, the SCR will shut off and it will not turn back on until another pulse is applied to the gate. It can also be a continuous voltage on the gate, but usually, and in this application as well, these are pulses being applied to the gate on the SCR. So this is a very large SCR. It's down inside the power supply. All of the output current flows through that SCR. It's very efficient because this SCR is either on or it's off. It does not operate in that in-between region where it's acting like a variable resistor, like a series pass element. It's not doing that. SCRs, again, they can turn on or off, fully on or fully off. So you can think of this as a switch turning on and off. So what's happening is the pulse that is applied to this SCR is a very precise timing from this voltage regulation control over here. So as these pulses from the bridge rectifier are occurring, if the SCR fires very late when one of those pulses happen, only a small pulse, or basically a small amount of current is able to flow, a small amount of voltage comes through. But if the SCR is turned on earlier in the pulse, then you have a much larger voltage that's able to build up over here, okay? It conducts for a longer time, more current is able to flow. So the timing on these pulses is the key to the voltage regulation, whether they happen earlier or later in the pulse, cycle that's coming out of the bridge rectifier, all right? So which is why there's no filtering up here. The filtering occurs down here, and at this point, the voltage builds up to a continuous DC value. You're not seeing that pulsating DC that keeps returning to 0. Because every time the pulsating DC here returns to 0, this SCR shuts off. And that's very important that happens. This SCR cannot continue to conduct. It must turn on and off. So this SCR, as we follow down here, the output, or the negative cathode right here, comes down. You can see the bulk filtering capacitors right here. We have the amp meter right here on the front panel. There's a shunt resistor right here, so most of the current flows through that shunt. A voltage is developed across that shunt, which is what drives the DC amp meter. And then down here is the main positive output. Now right here we have another SCR. This is that very large power SCR at the back of the power supply that we previously saw. And this is the Crowbar circuit. So what happens is if there's an overvoltage condition, a pulse is applied to this SCR, it conducts, turns on completely, and it basically shorts the positive over to the negative side, okay? So it's basically a short on the output, which clamps the output. The power supply is forced to draw a heavy current because now there's just a direct short, and then that forces the circuit breaker to open up. So basically a brute force way to shut down the power supply, but it functions very well as long as the other components are suitably rated because they have to handle a very high current spike. If you noticed in the earlier part of the video when the power supply tripped off, this SCR was firing, and you can see the current meter right here is prior to that SCR. So when this SCR fires, this meter indicates a very heavy or high current, and we could actually see that did actually happen. So that's how I know this SCR did fire and shut down the power supply. Here's the DC voltmeter right here. It's just across the output. Okay. This is a connector on the back panel. There's also some terminal studs on the back of the power supply for the loads to be connected to. Up here, there's a very large inductor in the power supply. It's rated, it says 51 amps. It's a 50 amp power supply. They rate this as a 51 amp DC inductor, 2.5 millihenry. It's a very large inductor for filtering. In the voltage regulation circuitry over here, we can see this portion over here is for the over voltage control. You can see from this transistor right here, if we follow this out, it comes over here, that comes up and into the gate right here on the crowbar circuit, or the SCR that acts as a crowbar. The rest of the circuitry here is for the voltage regulation control. Right here we have the two variable resistors. These are mounted on the front panel, and they're for the voltage voltage setting within the power supply. But they're basically setting a reference voltage for the voltage regulator. So what happens is the voltage regulator has a reference voltage, and it monitors if the output voltage rises above or below the reference voltage, then it changes the firing phase angle on this SCR. So it fires either sooner or later, and then that in turn affects the output voltage. Now right here you can see right down here is a power resistor. This is a very large power resistor that we could see in the top of the power supply. And it's just connected across the positive and negative outputs, and it's just a fixed load in the power supply. So if there's no output connected, no load on the output, this is just a continuous load inside the power supply, and it stabilizes the operation. This power supply would not be able to regulate very well if there's absolutely no load on the output. It does need some load all the time, and that's assured by this power resistor right here. So now let's take a look at the circuit board again on the voltage regulation circuit board, and I'll show you the issues that I found on this board. So I noticed a couple of repairs had been done on this circuit board. Over here, there's a diode over here and a diode right here that had been replaced. Now this circuit board has a conformal coating on the front and back, and that conformal coating has been disturbed under these components. So I can tell, you can see right there, there's a little bit, you can almost see of from where an old diode used to sit below right there. So I know that's been changed, and the same thing has happened up here. So this conformal coating, you can kind of see that shine that has. That's basically, it protects the components and the circuit board from moisture and other contaminants. Also not the most fun thing to work on when you're desoldering. That certainly gets up into the desoldering iron. That conformal coating causes a problem. It's not real fun to work with. It's pretty much all over all these solder connections in here. So something else I noticed is that this connector right here is kind of dirty, needs to be cleaned up, and I'm sure that the connector down in the power supply also needs to be cleaned up, so I'll certainly do that. If there's any loose connections or intermittent connections here, it would definitely cause a problem, so it needs to be taken care of. This capacitor right here has a broken solder connection on this lead, so that's certainly a concern, needs to be taken care of. That's this solder connection right here. So there's a crack, it's completely broken all the way around. So I examined very closely all of the solder connections on this board. Some of them are cratered and need to be reflowed, so I'll do that as well. The only actual broken solder connection I found was this one right here. Now, I'm going to change all of the capacitors on this circuit board. I'm not sure the age of this power supply. It's, I'm sure, possibly as much as 40 years old, something like that. These capacitors appear to probably be original, except for this capacitor here. I think it has been changed. There looks to be possibly some old damage on the circuit board. You can see right down in there. It looks like the board may have been pretty hot at one point, so this capacitor may have failed. You can see right there, it looks like something has happened. This capacitor, although it's a replacement, it has some corrosion on this lead right here. But again, I'm going to change all of the capacitors. These are electrolytics right here, okay, these three. And with the age on this power supply, they should be changed out. This is a tantalum capacitor, generally quite reliable. I'll go ahead and change it just because we're in here working. This is a polystyle, it's a metal film capacitor, but typically, again, quite reliable, but I'll go ahead and change it just because it's has a broken solder connection, so I'll just put a new capacitor in there. These 3 poly-style capacitors over here, again, generally quite reliable. This capacitor here is very critical to the timing circuit in the voltage regulator. I want to make sure that it's functioning correctly, so there's no sense in, guessing if these are good or taking them out and trying to test them and, reinstalling and all of that. I'll just put all new, very high quality capacitors in the circuit, and then we'll know that things will be in good shape going forward. So I will continue on with those repairs. One other thing I should mention is I did test all of the diodes in here. All the diodes test okay. I also tested all of the resistors. I tested them in circuit and accounting for any other components around the resistors, that can affect the readings, but I did not find any resistors that had wildly drifted out of tolerance or had any readings that were indicating any kind of opens or shorts or anything like that. So I don't see any other issues going on with diodes or resistors. Changing out the capacitors would only leave some of these transistors. There's only a handful of transistors right here. And if there's any further problems, then we'll have to look at those transistors. But for now, I'm not going to worry about those. I'll just change out the capacitors, and then we'll continue on and see if that solves the problem or if there's more troubleshooting to do. So I'll be back when the circuit board is repaired. Here's the DC voltmeter from the front panel on the power supply. Now I noticed that the meter movement was sticking and not indicating correctly, so let's take a closer look at it and see what the issue is. Now here's a service tip. If you're working on an analog meter, you need to know what the full scale deflection value is. So this has a scale that indicates 0 to 50 volts. However, that scale is not always what the full scale deflection actually is. So if you see a marking down in a corner, maybe down in here or something over here that says FS and then a number, FS for full scale, the value might be 1 milliamp or it might be 50 microamps or something like that. Typically it's a very small current amount. That's the actual full scale deflection. So if you have a meter that's rated at 50 microamps full scale and you apply several volts to whatever, let's say it goes 0 to 100 volts and you apply 100 volts to that meter, you would immediately destroy it. So it's always very important to know what that full scale value is. Now you can use an ohm meter from a digital multimeter. You can set it to the ohms function, and in the ohms function the meter will output a low voltage, and you can use that low voltage, and then oftentimes in addition to that you may need a series resistor to still limit the current, but you can use your meter as a power supply in testing a meter that has a very low value for that full scale deflection. So that can come in very handy. You can also use a DC power supply and an appropriate series connected resistor to limit the current. Now this is a direct reading type voltmeter, so it means that if I apply 20 volts to it, it will indicate 20 on the scale. If I apply 50 volts, it will indicate full scale at 50. So that makes this one pretty simple to test because you can just apply the direct voltage to it. So I have my power supply set to 20 volts. I will connect on the back here the leads, and it's like so. So you can see just in bumping it a little bit there that came up. Okay, so I have 20, the power supply is set to 20. It's reading pretty close to 20. It's off by a little bit there. Let me turn the power supply off. So you can kind of see it hangs just a little bit there. It doesn't really return to 0. So that should come back down to 0 if you tap that a little bit there. See there, it was sticking before. Let's see if it sticks again here. Okay, there it's stuck. All right, so I have 20 volts applied to it again, but you can see it's not doing anything. And if I come in here and tap it, it's clearly sticking down in that lower area right there. I'll slowly bring the voltage down. So that's 14, 13, 12, 11, 10. That actually doesn't look too good at all because that's really pretty inaccurate down there. Let's see if I go back up. It's kind of odd. It looks like it's really hanging up down there. You can almost see the meter, it kind of goes down, it bumps against, like right there, it kind of bumps. So something's going on down there. Then it pops up a little bit. That's actually 13 volts on the power supply. There, let's see, 15 would be about halfway right there. And it's actually 17 on the power supply, so some inaccuracies on that lower part of the scale. That's actually 21 volts, and it's only about 1 volt off there. That's not too bad. Go to 25. So that's 26, so it's about 1 volt off there. Go up here, that's 30 volts. Down just a little bit there, maybe a volt or so. Okay, so it's not too far off on some of those values, but there's definitely a problem on the lower end of the scale. It's kind of odd because it really seems like it falls down and just becomes really inaccurate. So I think the best thing on this one is to disassemble it, to take the back cover off. So it looks like on the back here, a little bit of possible corrosion there, but it looks like an adhesive sealant. I'm not sure what's going on there. These grommets, unfortunately, they're like a rubber kind of a grommet right here where the terminals pass through. Is becoming very hard. So not sure exactly how that's going to come apart. These nuts on here are just where the wires attach. They actually don't hold those studs in place. So, however, it disassembles. You can see the screws around the perimeter here. So if I take those screws off, this back cover will come off. So I'll do that next, and I'll have to be very careful because there'll be some wires attached to those terminals, and I'm not exactly sure how those terminals remove from these grommets right here. I'll have to find that out. I don't see anything inside the meter. There's no indication that any water or moisture has gotten into the meter. There's no dirt inside of it, nothing like that going on. It looks very clean, which always, that's always a good sign. The zero function does work. If you turn that, it moves the mechanism back and forth where you zero the meter, but because it's sticking, the actual needle doesn't really move, but the mechanism does move inside. So I'll disassemble it and we'll continue on. Okay, you can see the meter is now partially disassembled, so I have the front bezel and the window removed. Now I didn't remove the inner mechanism or the movement from this outer housing because to do so would require disturbing the grommets on the back of the housing where the terminals pass through, and those rubber grommets are just as brittle and hard as glass, so if they crumble or break, the whole meter would be rendered useless. But it looks like the problem was solved by just gaining access to this front area right here, so I'll explain what I did. So first I noticed that the meter movement had a lot of excess play and movement within the pivot, which is affected by this adjustment right here. So not this slot adjustment, but this little screw right there. So very, very slight adjustment, to the screw tightened up the pivot and it got rid of the extra movement that the meter had. So the binding and the sticking that the meter had at the lower range over here, it seemed to correct that. So it definitely improved things, but the meter was still hanging up about mid-scale. What I noticed is that the needle was actually touching the face of the meter about mid-scale. So if it kind of got past that, if you nudged it just a little bit, then it was okay over here at near full scale, and it was also okay over here, but in the middle it was touching. Well, this screw right here that attaches the face to the inside support within the meter, that's actually a plastic that's down inside there, and that plastic appears to have warped. So it's not broken in any way, but it's just warped, and I believe the face of the meter is bowed out just a little bit. So the only thing that I could see that could solve that was to bend the needle outward just a little bit. So very delicate movement. That's not an easy thing to do, but I was able to support the needle right where it makes a 90-degree bend right here, and kind of bends and goes down into the movement. Support it on one side, lift it up just gently out here. Was able to get just a little bit of a bend in that needle so that it cleared as it passed through the mid-scale. So now it's working very well. So with those two things done to the meter, this adjustment down here and then just slightly bending the needle just a little bit, looks like the meter is working, and I will turn on the power supply here. So my power supply is set to 20 volts. You can see it comes right up to 20, so the accuracy looks good there. If I turn the power supply off, you can see it just falls to 0, doesn't hang up or have any issues there. Now, if I increase the power supply, just start going up here, we can see it. It's up to, there's 30 volts on the power supply. That looks very good, so it's right at 30. Now again, this power supply that this will be installed in runs at 28 volts all the time. So 28 volts, it's going to be accurate on that setting. I lower this down here. So there's 28 volts. and you know, it's right on. That looks very good there. So it'll be, you know, something that can be trusted within the power supply, and the accuracy will be very good at 28 volts. If I increase this a little bit further here, we can go up here. Okay, so there's 40 volts on my power supply, and also looking very good there. And if I increase just a little bit more here, there's 50 volts on my power supply, and looks like 50 volts. So no issues with that. Let me lower the voltage down. There is one minor problem on the low end of the scale. Go back down here. So my power supply is now set to 10 volts. You can see it's indicating pretty close to 10 volts, so really no issues with that. But if I continue to lower the power supply down a little bit, okay, so now I'm at 9 volts on my supply. Well, you can see suddenly the accuracy isn't very good, and it's considerably showing less than 9 volts. So I don't think that much can be done about that. There's really no other adjustment. This slot adjustment that affects the 0 resting point in this meter, it really affects more of the accuracy, and I've played around with that a little bit. The 0 resting point, when the meter is pointing at 0, it's really resting against this little white stop right here, and then there's one over here for full scale. So this adjustment here, which then ties to this front, you know, adjustment that pokes through the window right here, where you can turn that with a screwdriver, it makes this slot right here move back and forth, which changes the tension on the spring. In many meters that will affect the 0 resting point, but again in this meter it's always pointing to 0, and it just affects the spring tension, which ultimately affects the accuracy. If you add spring tension or take away spring tension, you know, it'll read above or below the voltage that you're actually putting into the meter. So I did play around with this and was able to adjust it to the point you see now, where from 10 up to 50 volts it's very accurate, it looks very good. But under 10 volts the accuracy is pretty poor. So if I increase this in here, go back up, so there's 15 volts, you know, starts to come in there. That looks pretty good. And over here, this back up, there's 20 volts. You can see the accuracy, you know, improves very quickly as the voltage increases, you know, above 10 volts. But again, this power supply is going to run always at 28 volts. It really shouldn't vary from that. So if this meter, you know, is indicating something well under 28 volts, you know, it's going to indicate that there's a problem with the power supply, because when everything is working correctly, it's just going to always be right at 28. So the meter should be good enough now to put back in the power supply, because unfortunately it looks like this accuracy, we're just going to have to live with the inaccuracy, I should say, down there. But it's not going to be operating in this lower voltage range at any time in the power supply. So it will have to do. It's an odd problem. I'm not sure exactly why it's inaccurate on only that low range, but that's just kind of the nature of this meter. It certainly has some age to it, so something, you know, may have aged or just is out of calibration and just can't really be restored at this point. And again, further disassembly I think would risk damaging the meter, so I'm going to leave well enough alone at this point, because it will work in the range that's important for the power supply. So I'm going to reassemble it and we'll continue on. The voltage regulator circuit board is now ready to reinstall in the power supply, along with the front panel voltmeter. It's interesting to note how much smaller some of the new capacitors are compared to the old capacitors when these new components meet or exceed the ratings on those old capacitors. So I'll get the circuit board installed and power up the power supply, and let's see if it functions correctly or if more troubleshooting is needed. Alright, here we are back in the communications shelter. I have the voltage regulator circuit board installed in the power supply. I've put the top cover on the power supply because that interlock switch needs to be held in place. So the top cover is held on by just one screw right now, and I've done that just in case I need to get back inside the power supply for more troubleshooting. I don't want to put all the screws back in place just yet. And also the front panel is closed up, but just one screw is also holding it closed. So let's go ahead and power up the power supply and see what happens. You can see the digital voltmeter to the side. That's connected to the output of the power supply, so we'll be able to monitor on that, as well as the voltmeter on the front panel. So I'll reach over here and turn on the main breaker. The breaker on the power supply is in the on position already. Here we go. Alright, not too bad. Looks pretty good there. 28 volts on the digital voltmeter. And it looks like the main voltmeter came up and is indicating correctly. There are no loads connected to the power supply, so the amp meter is sitting at 0. You can hear the fan running inside the power supply. So that's looking very good at this point. I'll go ahead and let the power supply sit here and run, and I'll turn on a couple devices that are in the shelter that'll put a load on the power supply, and I'll let it run for a few minutes. And if everything looks good, I'll come back and I'll report on what I found out. The power supply has now been operating for about a half an hour. There's been no issues with it whatsoever. So you can see it's outputting a 20 amp load. There's several devices connected to it. You can probably hear them running in the background. It's kind of noisy in here right now. So the voltage is stabilized. There's been no problems with that over voltage condition. You can see it's operating 27.8, and that's right within spec, no problems with that. Alright, I turned off some of those external devices because it's pretty noisy in here with everything else operating, so the power supply just has a very light load on it at this point. But the power supply has been operating for close to an hour now with no issues whatsoever, so it looks like the fault has been taken care of with that over voltage condition and the fluctuating voltage. So the power supply is ready to put back in service, and the repair has been successful. So if you enjoyed this video, don't forget to give a thumbs up, and if you're enjoying the videos on this channel, please remember to subscribe. There'll be more videos like this coming in the near future. So thanks for watching, and until next time, take care and goodbye.